Hello, everyone, and welcome to Handmade Hero Show, where we code a complete game live on stream. We are going to be doing some lighting today. Before I get started, obviously, if you've seen the banner, we're doing a Kickstarter right now for our comic. If you like comics, please check it out. That's what that little fellow's doing up there. That's what Meow's doing right there. All you got to do is click on it, and it's got a trailer and all the information and all that stuff. So please check it out. We're just going to hop right into it today. We're going to go to probably the blackboard first, I'm going to guess, because we got to talk about what it is that we're actually going to do. We did some analysis yesterday, and I'm pretty sure I understand now, like, sort of what I need to do to my routine to do it, to make it do what I want it to do. If you remember, what we ended up with is, and I'll run it here, and I guess I'll show it here as well. Let me go grab the lighting code. So here's the Raycaster. So if you remember, we took a look, and I was just playing around with this routine to see what was going on with it and looking at some stuff. And by analyzing the routine just to figure out what was going on in here, I was like, oh, right, we kind of need to be more systemic about how we do this if we're going to switch to doing a KD tree, because we build a KD tree right now, we don't really use it. We use it as if it's just an AAB hierarchy. If we actually want to use it as an AAB tree, we're going to have to start getting smarter about how we do things, and we're going to want to do a little bit more careful work with how we handle our hit detection. So again, just to remind everyone where we're at, if I go ahead and run the HH Light Prof routine, you can see here that we have a way of sort of pseudo-validating our stuff by looking at what our textile error ends up being. So we know we don't regress on our hits much. And then what we can do is we can look at the total seconds elapsed. This is just us running our raycasting a lot to see how long it takes. And we want that number to go down. Now, ideally, we'd like to get that number to go down a lot, right? Like, we'd like that number to be going down to, 3 or 2. Like, we'd like some really massive improvements in speed if we can get them. And we don't actually know that we can. But we do have some suspicion, at least, that we could, because, we at least know that we're not doing anything particularly smart in here other than the fact that we do trace 4 rays at a time. So we have SIMD, and we have a reasonable box collider, but we don't really have anything else particularly smart going on in there. Now, one thing that I might want to do is start printing out the leaves and partitions information, because we actually gather this information, but we don't use it. So one of the things that you can see, in fact, if we go to handmadelighting.cpp, what you will see is that in the internal lighting core, which is here, what you can see is we actually compute this information. So we do these work casts initiated. We tally all this stuff up. And then in end lighting computation, we print it out, right? So we have a thing that does the tally here. We can do that ourselves, right? So we can actually do this inside the test routine as well. And what I'd like to do is just start printing out what those numbers are so that we have an idea of how much time we're spending in each loop roughly. It won't tell us exactly how much, but if we assume, it'll at least tell us like how many things we're processing in each case. And so if we take a look at the actual HH Light Prof code, and we take a look at after we do that dispatch, right here where we get outside of the routine, so we're done doing the lighting and we're ready to print stuff out. What I can do here is I can actually summarize. So basically, like here, I can take a summation. I can do a summation of the work count. So you can see we actually initialize these or create a certain number of these, right? You can see like alloc work count, this sort of stuff, right? And I don't remember, I feel like this is supposed to return the work count, probably. Internal lighting core. Yeah. So the actual work count that's done comes back here. So we can just sum the work count. We can sum the work count right here. We can sum all of these various values. And if we do that, we can then print out some of the information that we get. So we can say, look, here's the information. In fact, we can do that we can actually do that perhaps even as a matter of course. Now I think about it. So like if we want to, right, we could do this. We could say we'll always summate it. We'll put it in here, right? And then we'll print it out as part of the like performance estimate, right? So in here we'll print it. Now I hate printing. I hate actually using the code to print 64-bit numbers. It's always terrible because it was like designed by people who had no idea what they were doing. And so I'm just going to print these as float, even though they are not float, right? So what I'm going to do is I'm going to take like total cast initiated. Actually, I don't care about that. I just want total partitions tested and total leaves tested, right? I just want those two numbers for now, like partitions and leaves, right? And what I'm going to do is I'm just going to cast those to doubles on the way in so that we just have a printout for them that doesn't rely on weird format specifiers. So I'm going to go ahead and compile that and see if I can get this printing out just information for me about how many things we were doing. And so when we do this, what we should see is on the performance estimate, we should see how many of these things we do. And so over the repeated runs, you can see it. You know what? And the other thing too, I think I might print this out in both cases. So whether or not we're doing the performance or not, let's print it out in both cases. Because that way I can also see how much a single run is versus multiple runs. Just easier to look at. So if we take a look at that, you can see like, here's how many we're doing on a single run. Oh, wait. We re-zero them every time, so never mind. Yeah, we don't need that because that is for a single run. Duh. It's not multiplied out. All right. So that's just telling us like how many partitions we're testing versus how many leaves we're testing, right? And we also had a partitions per leaf value that we were printing out in the lighting, and I think we want that because that lets us know like how many partitions it takes us to get to the actual thing we want, which is leaf testing. So what we want is, well, you know what? I guess maybe I don't care now that I think about it. But if you take a look at the ratio of these numbers, I guess, which is sort of what I was talking about, you can see that like actually this one is almost 4 times, more than 4 times. Yeah, I think it's more than 4 times. Is that right? I'm going to print it out. I just said I wasn't. I'm going to print it out. So this is the partitions per leaf. I don't know why I put K in there. There we go. So what I'm going to do here is just like, here's our total partitions tested. Here's our total leaves tested. So I'm literally just going to take this and I'm going to divide, right? And I think we have a safe ratio. Well, actually, I don't know if we have one for doubles. And since we know this is never 0, I'm just going to do it, right? So now this will tell us the total partitions per leaf, and you know this one probably wants a little more precision. So this one probably wants more like 0.2 or something, I'm guessing, just so we can get a little bit of significant figures in there. So if we take a look at what this does when after we run the test, this tells us that we're how many partitions, how many leaves. This says there are 4.4 times as many partitions tested as there are leaves tested, right? So a couple numbers we care about, right? We probably also care about the total, right? So we might want to just do like this, where we do that. So add them together. And now we know like the total amount of work we're doing, so the number of like actual loop bodies, which is this number here. We know how many of them are being tested just for like culling purposes, which is this number here. We know how many of them we're actually testing and using results from. So like these are actual boxes. We do the collision and we potentially update our closest point. And then we know like what the ratio of those two things is. And so that's pretty much all the information that I really need there. What you can see is it's like, okay, the total number of loop bodies is 2.8 million, right? Which is a lot of loop bodies. And you can see that's why this is so slow, right? because our routine isn't that slow. It's just that's a lot of stuff to check, right? And so the question is, where's that stuff mostly coming from? We could see it's 4 times more likely that what we're doing is testing a partition. So we're spending a lot of our loop bodies in partition testing. We don't actually know that that's the bulk of the time because we're not timing the 2 loop bodies separately or anything like that. But we do know that we're just executing that loop a lot more. And since the 2 loops look similar, and if anything, this loop is more complicated because it has to push stuff on a stack, it's a pretty fair bet that, like, that's a really bad part of the routine, right? It's called way more often. It's called almost 5 times, 4.4 times, over 4 times more often. And it's probably more expensive. So we kind of know that making the partition tester smarter or better, using less partition testing, or, doing something smarter there, right, could make a big difference in our routine. So I think that's what we probably want to focus on. And the first thing that I think we should probably try to focus on is just simplifying this down so that we don't actually, I think we should try to make a special purpose design for the KD tree. I don't think we should stuff it into the AAB like it is being stuffed now. Now, we can still store it uniformly if we need to, but we're going to want something better, I guess is what I'm saying. All right. So what are we going to do? Is the real question, right? So what are we going to do here? We need to try and figure out a solution here to our situation that'll improve the partition testing in some way. So if we actually take a look at the partition tester, so if I go to my raycast here, I'm going to need to figure out excuse me. Sorry. I'm going to need to figure out some way to change this routine here to be able to do what it's doing faster. And one of the things that I want to be able to do here as well is, like I was saying, we need some way of, let me just go to the blackboard. We need some way of processing the hits in order so that we don't waste time processing things that we know we can't hit. Or another way to say it would be, we need to make sure we don't waste time processing things which we know won't be better hits than hits we already have. So if I actually load up Milton here, and I just drop in a day 595, so is that actually the right day? Seems low. Was it 594 yesterday? Yeah, I guess it was. It doesn't look like that's quite up yet. The new one. Begging lightning validation, 594. Let's see here. Actually, you know what? I just don't want to write the wrong day down. So the video that we last posted was 594. Yeah, okay. No problem. No worries. All right, so if we want to do a KD tree here, which is what we've constructed and how we are actually processing it right now, we're just not aware of it, meaning our routine is processing it as if it's an AAB tree. So in other ways, we built a KD tree, but we test an AAB tree, right? So normally a KD tree is a thing that just splits in one dimension every node. So if this is like my node, and I'm going to have like a and B branch here or something that I go down, the way that it splits space is, you've got a bunch of objects in the space, and it picks a split plane and it sorts them into an A side and a B side, right? And so a KD tree is just doing that recursively. So then you take the A space and you split that, right? Split that, and so on. So you only split by one dimension at a time, X, Y, or Z. And that's the entirety of the idea behind a KD tree. What we're doing is we're building the tree that way, but then we actually store these as boxes. So we don't ever take advantage of the fact that the entire information for a node can really just be one plane. And when you test against it, you don't need to test against a box. You could just test against that plane and know what you were going to be doing. So ideally, what we'd like to do here is be cognizant of the fact that this is a KD tree, because we could probably speed things up if we did. And one of the things we'd like to do, because obviously we can start by just doing a plane test and working with the plane, because what we could do is say, well, look, if we have a plane and we classify which side of the plane we're on, right? That's very easy to do because it's just the plane equation, right? So whatever the plane is, we know that the plane equation tells us which side we're on. And because this is axis aligned, we don't even need to do an inner product, because we know that whichever axis it is, right, X, Y, or Z, whichever axis it is, we just use that value, right? That value minus the D value of the plane is going to tell us which side we're on. So it's literally just a subtract of one of the axes from a constant value. That's it. Right? Super, super simple. So we know we can test which side we're on really easily, and then all we have to do is see the same thing for the Rae direction. So whatever the Rae direction is, we can classify which direction we're going, and if we're not going in the direction that would point us towards the plane, so if our Rae is pointing away from the plane, we know we only have to test the side we're in, right? We never have to test the other side. If we're pointing towards the other side, then we need to test our side first and then the other side after, right? And so the problem that that we have here is that we have to sort of create a stack that would be more amenable to that process, because right now we don't really have a stack that can do this. We don't have a stack that allows us to do all of our work, and then when we pop back up, actually, yes, we do. Never mind. We can do that easily. Okay. So we just push this on the stack first, and then we push this on the stack. And then it will pop back to this eventually, right? So totally fine. Okay, so that's one thing we can do, and that would be easy, right? So that's simple. And then the other thing we can do is, if at any time we can pre-test and say, look, if there's no way I can make it to this plane, so whatever the distance from this plane is along the Rae, and that's an actual intersection, so that's harder to compute because we have to know the actual t value. Wait, no, it's not. No, it's not at all. Never mind. So even that's easy to compute. All we have to do is just add our current t min values, like our hit, add our current hit value. If we just take our Rae, add our hit value to it, we will get a point. If that point is actually on the if that point is on the other side of the plane, we know that we could hit something on that side of the plane and be closer. If that point is on the same side of the plane as us, we don't have to do that branch at all, right? Because we know at that point that the value that nothing we could hit on the other side of the plane would ever be a closer hit than the hits we've already had, right? So we could do a lot better potentially here. And I don't want to say definitively that this will be faster because I don't know. Like anything on a modern CPU, unless it's a very clear-cut thing, you can never say that you're going to be faster when you do something. if you already have a routine that's relatively optimized, meaning, you know, you've done the work of putting it in SIMD and it's not doing anything incredibly stupid, then even though you can have a suspicion that, well, this should be faster because I think it can do less processing and it can do less math, so that should equal a faster routine, right? It's just intuition. It's not true until you actually test it and verify that fact, right? So I suspect that this will give me a faster routine, but that is purely a suspicion. It is not actually any guarantee. So we, again, want to take this cautiously and say, all right, let's try to do this by replacing this routine, but we're going to leave the existing routine in place probably because we don't actually know yet whether it's going to be faster, right? So this routine here that this part here, we're going to have to replace. Okay. So what we need now is we need a way of encoding exactly what I just said into our stack. So we're going to have to pull something off the stack that we can actually use in some way that gives us a bunch of values. And the values that we need are going to be like, you know, are going to be, how should I say this? So I want to write this routine first and play around with it before I go modify my stack because I don't know exactly what I want to store. That's what I'm trying to say. So let me sketch out all the things I just said, like how would they actually have to work. I want to try and do that first so that I have like a solid thing where I can be like, okay, here's what I'm going to have to do. Now let's design the stack that gives me easy access to those things, right? Okay, so if we take a look here at the things I'm going to need, I need to know which one of the values in the plane I actually want, right? Because what I'm going to need to use that value as the classifier, right? I need to load out of my source data, my Rae or whatever. I need to use specifically the value that corresponds to the correct dimension. Now, the problem that I'm going to have here in terms of making this fast is, you know, I would like to avoid doing something like a horizontal add, and I don't really need one because, like I said, doing a dot product with something where you actually know already it's just one of your values, either positive or negative, I just am not sure. I'm not sure what the fastest way to do that is with an intrinsic, because while it's easy to pick a dimension, I don't really want to have to branch every time. I would like to be able to load using a value, and I'm not sure you can do that. So if you take a look, for example, at the extract routines, like here, right, you can see that they're set up around immediates, and that's the problem I'm talking about. So, for example, yeah, let me, what do you call it? Let's go here. So what I want to do here is, like, I guess they could be swizzles. They could be, wait. No. It's not as bad as I thought. Actually, I can just do this with some constants. Because now that I think about it, right, we already have our Rae as X's, Y's, and Z's. Because we're 4 wide. So actually, I don't have to be as nervous as I thought. It is a little annoying because in order to avoid branching every time, I would need to basically do like 3 instructions to select the actual one that we need, right? But it's okay otherwise. So I think we're actually all right here. So what I can do is I can say, all right, we've got a couple values we want here, like I was saying. We've got like a classifier. So this will basically be the thing that says, for this particular plane, what are we going to do? And what I need to do here is I need to do like a select, effectively, right? I need to be able to pick based on some kind of a thing that's stored in the actual stack. I need to be able to pick from X, Y, or Z. And yeah, I don't know if we actually have that. We do. So you can see here I've got like select and then I've got a mask value, right? So what I need to do here is I need to do a select and then I need to do another select, right? Is how this would work. And so the Rae position, for example, like where the Rae actually is, I can generate here. So what I need to do is say like, trying to think of what the fast way to do this would be. So what I need to do here is say like, okay, you know, the Rae direction or the Rae position, right? So I've got Rae Origin, I believe is what it's called. This value. So I've got Rae Origin and I want to select from like the X value or the Y value, depending on like the mask that picks one or the other, right? So I want to do this with like an S mask. And then I want to do here another one that's like, okay, I've got classifier, or I guess maybe we'll call this Y mask. And then we have a Z mask, right? Rae Origin Z. And so this is just doing a dot product by doing two selects, right? And again, I don't know if that's a smart thing. It may be that we really would rather just do the multiply add, which is two instructions, but issues on two ports. Not sure. Hard to say. Actually, because the select... Yeah, I guess we can worry about that later, but... Yeah, hard to say. But anyway, if we have the Y mask loaded here and the Z mask loaded here from our stack or something, or actually be from the box somehow, right? We would load those up probably by just loading a single floating point value and replicating, right? I would assume. So that's probably how this would work. It would be like, you know, our KD node here, and we would say like whatever the Y mask is and whatever the Z mask is. Those would just be stored as two floating point values that we would load for expedience. So I think that's all that would happen. We then have a classifier now that we built that can pick out the thing we want. And so we can do that twice and get, you know, the basically like the origin class, or like the origin side. You know what I'm saying? And the direction side. And this will just pick based on the Rae direction instead of the Rae side. And I don't remember, it's just Rae D, right? Yeah. So this tells us where we're starting. So relative to this KD tree, like which side we're on. And then it tells us like whether we're going to stay on that side or not. So basically, if these two sides are the same, you know what I'm saying? And actually, I suppose we can also, we can classify a little bit differently. Rather than using the Rae direction, we can actually use our current tmin. Like I was saying, we can step out to our current tmin and use that. So another way to look at it would be, instead of doing Rae D here, yeah, we can just use, yeah, we can just use a slightly different value here. And since we can do subtract as well on this, there's some other things we can do a little later. But anyway, so if we go in here and we take dir side, right? This is actually going to be like end side, I guess. And so I might call this like the start side, you know, and the end side. because it's like where the ray starts and where the ray ends. And so what we'd want to do here is not ray D. We'd want to do like ray end. And ray end is just going to be like an add, right? So it's going to be like a v3-4x ray end equals Rae Origin plus whatever the current like minimum value is, right? So it's this, right? It's this. Now, since I think we do probably want to know that value fairly frequently, we may want to start storing that, right? So the hit P, we may want to stop caring about T-ray at some point and actually start caring about hit P, but I don't know. We'll see about that. So this is actually what we need here. And so we produce that, and on here we're going to do like, okay, so hit P, right? Hit P, hit P. So that's all fine, and I think that gives us the actual information that we need. So this gives us our origin point, this gives us our hit point, so we have a start and our end. And the only thing we need to do now is actually subtract. So we need start side to be like, you know, start side minus, and we need end side to be end side minus some like plain D value, right? And this is just the thing that we're using to adjust, so that we know that if we just did this, we're just picking the coordinate, but the plane is somewhere in that, along that axis, and we have to remove that value so that we're relative to the plane, right? Now, the fact that we're subtracting this from both things means that I'm not sure we actually need to do that. We'll see as the math goes. If it might be that we can just ignore that, but so from the box, from the like permanent storage of the KD tree, we would need to know the masks for Y and Z and then the plane. And then from those three floating point values, we can produce exactly the thing that I said on the blackboard. We now know what side we start on, what side we end on, and we can tell what the sign of those two things is if we want to as well, right? Which is probably what we care about for testing. Okay, so that's the actual information that we needed. And now we just need to figure out what exactly we're going to do. And like I said, there's only three things we might want to do here. We might want to push both things on the stack, or we might want to only push... We either want to push both things or no things. I'm sorry, we either want to push both things or one thing. Technically, there's a case where we would push no things, but in order to know that we wanted to not push anything at all, we would need additional piece of information, which is the the minimum plane bound, or if there's other bounds we wanted to check. So basically, the question is, do we want to do that or not? And what I mean by this is, if you take a look at how the KD tree is structured, what's going to happen here is that, let's suppose we have a bunch of crap, right, scattered around. We do a KD tree division, right, and we're going to do a raycast like that. Well, if we were to do this testing in AABB land, we would have two AABBs to test against, this one and this one, right? And what we would find pretty much immediately is that we don't actually need to test either of these two things, so we would just never descend. Once we go to a KD tree, the only thing we're going to have is that we're on this side of it. We're not going to know that actually we don't need to test it because the bounds of it are not close to us. Now, what we normally would do in a KD tree is we just keep going, right? There's another bound, there's another bound, like there's another bound, there's another bound, right? And so on. So we would always go down and test at least one thing for every raycast, even if we're casting outside. That may just be better. It's hard to say, right? The idea behind a KD tree is minimize the number of actual tests like that you do to walk down to leaves and then test the leaves, right? So what we want to do is keep this as simple as possible. And again, like, I don't know if it actually is. You can see how much work we're doing here. It is a fair amount, actually. So it's unclear if we can beat it or not. Modulo our loads. Here's the actual work we're doing. Mostly the selects are the cost here, and then we've got two subtracts. So then what we want to do here is say, look, either we're gonna push two things or one thing, right? So that's all we really need to know is we're either pushing one thing or two things. And this might be a case for that conditional move, because in this case we know that we'd always be pushing one thing. So we know that like box depth plus plus is always going to be equal to like the close side, right? And then the only question is like, do we push the far side, right? So it's like this. Maybe it will happen, maybe it won't, right? And that might want to be a conditional move now, like I said, because unlike the previous routine, we need to do all the work to determine this. There isn't extra work that gets done because there's no binary and here or anything no binary or. I think it's just like literally we and these two things together, and whatever the result is, we push or don't, right? So we would do this classification, we would then, push this on, and we would just see, can we make it to the far side or not? If we can't make it to the far side, we just stop, and that's the end of the story, right? So I think that's it. I don't know. So in here, we basically say, okay, we got two box step pushes. We want to push a close side and a far side. The thing we need to know in order to determine so the start side, the reason we need to know the start side is just because we need to know whether or not we need to be able to select which of the two sides we're going to push, right? So the reason we need that is because we need to figure out what close side even is. So close side is going to be equal to like something that has to do with what start side sign is, right? So if that makes sense. So another thing that's interesting about this, now that I think about it too, is that there's only one of them. So interesting. So the Rae origin is the same for all of the rays that we pass in here. So we don't actually need to do multiples on this one, right? This is not actually 4 wide. So that's a bit of a brain teaser, isn't it? So the question is, if that's not 4 wide, what do I do with the rest of that? Yikes. So the problem that I'm seeing here, and it's not a problem as much as an opportunity, I guess, is the way to think about it, is that if I want to know for my KD tree which side I'm on, the Rae origin for all 4 arrays is the same. So it doesn't need to be computed wide. You're just computing the same thing multiple times. That's just kind of wasteful. So you're wasting 3 lanes worth of arithmetic that you could have been doing something on, right? And I guess I don't know, though, what could I possibly use those other 3 lanes for, because there's no real point to it. Now, I could classify 3 KDs at a time, Sorry, 4. And I guess I just should? I mean, yeah, I really don't know what to do there. I'm sure there's a right answer. People use KD trees for ray tracing specifically. Like, this is a very common technique. So I think I must be doing something stupid or not thinking of something obvious, because I'm not sure how you parallelize that particularly well, because it's like, well, the origin's in the same place. And when I want to classify that, how do I avoid throwing away the work there? I could classify this against it and its children at the same time, but if I do that, what do I do for push purposes? I really don't know. That's a stumper. Why is what was my computer just doing? It just did a little like waiting for. I don't want to know what that was. That's a real stumper. So I don't know what that implies. So I guess the answer for me here is, I guess I do want I guess I do want to put some more information into this thing. Like, if I'm going to have to classify the origin of this ray relative to something, I might as well classify it relative to 4 things, right? And if I'm going to classify it relative to 4 things, I might as well classify it relative to like 2 bounds, like a min and a max bound, at the very least. Right? So I guess what I would say is it'd be pretty easy to switch this to using 2 of the lanes. Using 4 of the lanes, I don't know what to do with that. I'm really stumped. So using 4 of the lanes would suggest that we would also need to test a second axis at the same time. So like we could always include z bounds and just like we could use some kind of weird hybrid tree. It's like a alternating XY tree with z encoded on every rung because you can. Yeah, I'm sorry. I'm stumped on this. So I want to go read some KD tree literature at this point, which is what I would normally do. I mean, I would have normally done that first, but I do try to always figure things out myself on Handmade Hero, just to walk through that process for you. And it's a bummer here because I'm pretty sure people have already worked this out to within an inch of its life. So I know someone's doing something smarter than the things that I'm saying, because I can't imagine they haven't. They've definitely figured out better stuff. I'm just not thinking of what that better stuff is offhand. And so, like, yeah, filling up. So the good news is the far side point, like the end side, that obviously always needs 4 wide because the hit on each ray is going to be different. So that's not a waste of time. But the Rae Origin classifier definitely is. And I'm just not seeing what to do with that additional information. I mean, I guess the answer is just don't use it yet, I guess. I mean, I don't know, man. I just don't know. All right, well, let me see what happens if I go a little further with this, and I'll just say that this is the best we're going to do. It sucks. Sorry. So we'll do the crappy version, and then we will go just look at some literature on it, like what the current research papers are on fast, like GPU ray tracing, for example, would have talked a lot about this sort of stuff. And we'll do a better one from having read about it then, because unless I come up with a brainstorm soon, like, this is not smart, what I'm doing here. So once we select what we're actually doing, so once we select one of these things, we then can determine which side is the close side and which side is the far side. So we're going to load out of the KD tree, right? We're going to load something based on an address, like a 0 or a 1. So it would basically be like sides here. And we would use a sign bit, right, to determine that. So we need like a value that will either be a 0, or a 1 here, that will load which one the close side is, and then we have the far side is just the KD sides of not that, right? So this is like the close side index, and this is not the close side index, right? So just load the other one. Now, there's other things we could do here, and possibly that are possibly smarter. Another one we could do is just say, like, I don't actually know which way we want to do that, but like something like this, we'll see. I don't actually know how we want to do that, but basically, like, the not of that would be what we'd load out. Anyway, so if we load the far side and the close side, we would then push the close side on, and then assuming that like end side is different, right? We would push the far side on. But otherwise we wouldn't. And again, that's something we can try to make be, a conditional move, or at least give the option of a conditional move in here. So we could say, like, all right, if the end side is different, then we push the far side. Otherwise we don't, right? And again, I think that has to happen first. So yeah, this is going to have to happen first. So I suppose this would probably have to be an if at that point, right? So we'll see. Because the C move would be dependent, like this would be dependent. I don't know if we would really want that. It's hard to say. So if the end side is different, then we're going to push the other side to look at, first. and then we'll push our side and look at that. Now, there's another problem that I see here, which is that when we're looking at these, we would also want to, another problem that I'm seeing with this is this actually wants to be done before you look at this particular side of the plane. So if we assume what we're pushing on here is regions that themselves are divided, we don't need to test those. So this is a little bit squinky as well, right? Like maybe the right way to think about this is a little bit different. So maybe the right way to think about this is like, look, we're going to do a hit P here, and we're going to like take a look and see if we can reach this thing. Because we know which side, when we push something on, we have to kind of push on a particular side, right? We have to say like we're pushing on this side of this thing, right? And then when we actually go to test it, at that point in time is when we want to see whether or not, like, we don't want to push on a side, then do another side, get a closer hit, come back and actually test the other side, because we don't need to test the other side anymore. We've gotten a hit that's closer. So we would want this to happen earlier, right? So this is kind of more of a like this sort of thing, and this is probably more of this sort of thing. I'm guessing. So in other words, like, the only thing we're doing when we test a partition is deciding which side to push on first, and when we actually go to process one of the sides, that's when we would check to see whether we actually could get there or not. Right? So, you know, so we have to do this, right? We need to do a like, is this thing that I'm in right now, is this region reachable? And if the region isn't reachable, it can't push anything else on. If the region is reachable, it just pushes both things on, because the test for whether or not the far side should go on there is done later, right? So I think this is getting slightly more sensible. So let's look at this one more time. So I guess we just need to know, are either of these two things, is the start or the end, are either of them on the correct side of the plane? Right? So that's all we do. And if they are on the correct side of the plane, we push both. If they're not on the correct side of the plane, we bail. I think that's it. Yeah. Right? And this can just be like that. And I mean, those could definitely be conditional moves if we want them to be, but I'm not sure we do. Right? Yeah. So I think there's more we can do here, but that's what I'm zeroing in on. I don't know if that's really the smart way to do it. And the reason that I think it's not smart is, like I said, it just seems like it wastes too much work. to me. I'm not sure. Furthermore, there's another piece of information. There's another thing we can do here, which is we can just remember this value, right? So we can compute this and store it, right? So we can do like a thing that looks like this, where we OR in the like start side bit, right? And then when we get here, we can just do like, right? Because this is the Rae origin is classified relative to this plane universally. Anytime we look at this node of the KD tree, whether we're looking at the left side or the right side of the node, we know that the origin's answer is always the same no matter how many hits we've processed. Because unlike the ending point of the Rae, it doesn't change. The Rae origin is where it is. The Rae endpoint gets closer and closer to the origin with each successive hit. So that one has to be tested fresh, right? So once we produce a start side classification, we can just remember it. And then we just use it here, and we don't actually have to reproduce it every time. So I think the only thing we have to actually classify is the end side. So we have to load a Y mask, a Z mask, and a plain value, right? We have to produce where we think this thing currently is. And then we would just take the two bits and look at them together, right? So I think that's... So the only other thing I'm not sure about here is how we actually want to do the bit classification. So out of these things is going to come a sign, right? And that sign, you know, we could just do a multiply or a, we could have a multiplication value that we push on the stack that we use for that or something, but I'm not sure which one we want to do in that sense. But so we just need a way of knowing for each plane that we push on here, we need to know which side we were trying to do, whether the far side or not, right? So I suppose what we could do is just use an XOR to toggle this. And maybe that's the end of it. Again, just not sure. So when we load one of these up, it's going to have which side the start side was on. And because we know which one of these is the close side at this point in time, we do know how to classify that. So we could pre-classify this correctly. What we don't know when we get here is which side this represents in terms of end side. You know what I'm saying to you? So which way this sign bit should be tested is not clear. we would need an additional piece of information to know that, right? So that's the tricky part. And I'm also still not sure about the like testing the far side part of things. And the reason that I'm not sure about that is just because I don't actually know whether that's a smart thing to do. If these were actually region sides, maybe I need to make it so that actually you actually have the data stored in a side. You know, maybe that's just easier. In other words, what I could do is I could just push sides on here, and then the sides themselves would actually just have redundant information like, oh, you know, here's the plane and it's going the other way, and so you just load that up and it works. You don't have to remember that, right? But I don't know. And I suppose the other thing that I didn't do here is we don't always need to push both, because if the Rae is, I mean, I guess I'm pushing both because you're gonna test the end side either way, so it's like, look, it'll get cleaned up in the next pass. But I don't know if that's the smart way to do it or not, right? It may be that that's too wasteful, and I don't really know. All right, so let's walk through this one more time. If we assume we can load up these masks for what we're pushing on here, right? If we assume that the sides encode that, they're going to encode, I guess we could just have them encode. Yeah, I guess we could do that. So I guess we could just have the two sides encode which one they're doing. So I guess we would just do something like this. So there's like a test mask in here, right? We would figure out the end side. We would get the end sign out of here, right? Or by extracting this thing. And the same is true here. And then what we'd want to do is say, all right, so whether or not you're on the correct side is going to be determined by the test mask, which will tell us which one of these we want to do. So the end side bit and the start side bit, these are going to be XORed basically, so it would just be this sort of thing. And the start side bit comes from like the stack, right? Because that's something we actually, you know, that gets pushed on in here, right? So yeah, I think that's what we want. And I guess it may be the case that you don't actually need to do a test mask on the start side bit because that could already have been handled in here. So I guess really it would look more like this. So you'd have which end side you were on, and you need to test that, and you already produced the start side, which you know you're going to want to go down this one. So you're saying, like, look, always process this. And honestly, that's not even a start side bit. That's just basically saying, like, look, whatever the like start side bit is, whatever the like always process, right? You're gonna always process this value. And in fact, since you're always gonna process this value next, it seems like really this is where you should pull something off of the stack anyway. Right? Like the actual way that this should work in theory would be that the entry value would get pulled off the stack here. So this you would just assign, like this is the next person to process. So you just say like, here it is, right? Whereas this one would actually pull it off. I want to take a look at that. So let's suppose that in here where we've got this entry being pulled off the stack, I'm actually going to make that be the if zero. So I'm going to take a look at how this would work. So in here, what we would say is, look, man, we're actually going to just process this value. So we have something like our, like, you know, cur stack value or whatever, right? That's our weird thing that we're recording. That's like a packed magic thing, right? And we are going to do a while depth is greater than 0, right? So we do want to do that. And furthermore, it's really a do while loop. Like the depth is not 0 at the start. So we can just do this, right? When we come through here, we would do this testing and we would say like, oh, okay, like, you know, in here, we want to do, whenever we do our always process KD sides, whatever the heck we're doing in here, this goes on the stack. This doesn't, right? So this thing that we've got here is actually just the new cur stack value. Like, we're gonna process it, right? So we loop back through and we process it, and as we go, we're just always processing the close side. Like, we're just looping on the close side. And we may leave breadcrumbs for us to go back and process the other sides, but what we know is anytime we pull something off the stack, it is the far side, right? So we don't need to do this. Like, this testing actually is only going to happen when we pull something off the stack, right? So basically, if we actually need to grab something off the stack, so if we didn't hit and we need to grab something off the stack, we grab it off the stack here. And that's when we do this. Right? Yeah. Something like this, I think. So yeah, so normally we have something, we're going to be using the close side. So we would be looping on the close side each time. We'd get the cur stack value out. That's the one we're going to do. If we come through here and we pull something off the stack, we'd actually, the while loop would actually happen here, right? This is probably not a great way to structure this. Like, maybe this is stupid. We'll see. So in here, we now just need to search backwards on the stack for, so you know, maybe you could just even do this. So either we got something here, otherwise we search backwards on the stack until we find somebody. Until we find something to process. Actually, I guess that would be here. And I don't love that, right? It just starts to look too complicated. Yeah. I want to take a quick pause there because I just realized something. So I do wonder, should we change this around? So let's just take a quick look at this here. Oops. Did that end up being right? I don't know if it is. Is that right? There we go. So one thing I want to take a look at here is I want to see what the behavior of this thing is, how sensitive the current routine is to where we put those loops. So we're getting like 6.5 through here, right? 6.3, 6.5. Looks like 6.3. Pretty regularly, right? Yeah. So if I was to move this loop so that this loop actually happened inside, what would that do? So in other words, in here where we are going to do the push, so if we say, look, here's how we're doing this. We do a push on this where where we're going to push this on the stack. If instead of that, we actually grab this thing, right? And this case moves on to the inside. I'm just curious what that does. So basically, like, making that outer loop just always happen, and then there's a branch inside here, and this is the only branch, right? And I assume it should be the same, but I just want to know, like, will that change the performance in any reliably different way, or won't it, right? So what that would look like is, yeah, in this current path here, we would do this. So this is the hit test, right? And we would do the push in here, like this, right? So in here we would basically say like, okay, in fact, we don't even need that to be in the else container, do we? Oh, I guess we do, yeah. So we would just do like, okay, if should push and like whatever the thing is that we're about to push, if that thing is a, so this, if whoever we were about to push, which is like the box pack structure here, if that is a leaf container, then we just process it right up front. You know what I'm saying to you? Like that. And if it's not, then that's when we actually push it on. If that makes sense. So this would not be source index anymore. This would be like leaf index or something. And this would be leaf index as well. And then this would not be box. It would just be leaf. Ah. This is a real pain in the butt. Like, yeah, I know. What's your point? Like, I'm trying to use those again, but apparently that's like not good enough for you or something. Like, okay. You know what? This is ridiculous. I don't care that that hides it. What error is that? This is really annoying. Are you happy now, compiler? There. So I'm just curious what that does with the runtime. Like, I don't know if that should have like no effect or if it has a positive effect. Seems consistently pretty positive, right? So basically, like, processing something as soon as you can seems pretty good, right? Like, don't push it on the stack. I just wanted to know what that would look like. So not pushing something on the stack if you don't have to is like a plus there, it would appear. So, yeah, like, I'm going to get rid of some of this stuff here. So I'm going to assume this path is right. I don't need this anymore, really. So yeah, like iterating over the leaves in a loop inside when you actually go, okay, this thing is a leaf container now, so I'm not going to actually push it on the stack. I'm going to do it right away. It seems like that works a little bit better. It could just be because of code reorganization. Like, it's hard to tell without better profiling tools whether that actually improved things or whether it was just like, oh, the loop alignment's different now, or, you know, things like this. But, you know, it's worth noting. So yeah. So yeah, so what I would say is I think that means I do want to do what I was saying before, which is that inside the alternate version, what we would want to do is we'd want to look here and say, like, you know, is this a leaf container, right? And if it is, we would do our box testing here, right? So our box testing would go inside here when we determine that we're gonna process somebody. It would go in here, and then if it's not a leaf container, then we would do this nonsense, right? All right. So, yeah, looking at this again, so it's still a little bit confusing, and we want to be able to work this routine a little bit better. What the heck? Where'd that come from? There we go. It's starting to sort of take shape, but again, I'm not really sure it's in the right zone at the moment. It's still looking pretty wonky. I'm not sure I love it. I'm glad we sort of randomly got a little bit of a speed up there just from like, figuring out the fact that we could loop on the internals there. I also want to do let me do one other thing before I go any further than that. I also want to know what its estimated timing is. So when we do the profile run here, and we print this out, since we know what the repeat count is, I also want to produce the milliseconds here. So like something like this. Take the total seconds, divide by the repeat count, multiply by 1,000. Something like this. So we can sort of see, like, what do we think the frame rate of this thing would be? You know, how far away are we from good is another thing that, I don't know, just feels like we might want to know that. So, yeah, like, if we look at what the expected milliseconds is here, assuming that I did that correctly, right? It's total seconds over the repeat count. So that's like how much time we took over how many times we did this thing. That should give us the expected milliseconds, right? Now, what's weird about that is that looks way too fast. So, like, if we divide that by the thread count, which right now is like 6, so let me do this in double. That seems totally nuts. And possibly wrong. Although it could just be because of cache effects or something. So, I mean, looking at that, it would suggest that, like, somehow we're running at a speed that would be 60 frames a second already, even before I go try to fix this thing. But that's not the frame rate we're actually getting, although maybe it is. So one thing I don't know is, because I need a frame counter, and we should probably put one in, where if I don't do any of this, so I get rid of internal and slow, if I don't have anything else compiled in, I'm not sure how long whether we actually hit 60 frames a second or not, right? So if I actually load up Remedy now and run ourselves, here's Handmade Hero. I don't actually know if we hit 60 frames a second. I don't think we will, but I don't really have a way to profile the frame time outside of this. So what I think we need is a way to put the frame time up here in a way that won't, that is just always available, right? Like, so also that should not be possible in an internal build. In case anyone was wondering. So we got some work to do to remove that stuff, right? I mean, like, you shouldn't be able to pop any of that up in an internal build, so that's a little weird. But so we need some way of printing out what the actual frame time is, and I suppose there's other ways that we can do that too. Like, if we want to, we can probably use like Nsight or something, and just ask it to tell us what our frame rate is, right? And that would be like a unbiased external measurement, right? Just to see what happens. So let me try it and just see what happens if we run this using the frame profiler, and just see what it thinks, right? So you can see it thinks we're getting like 21 milliseconds a frame, which is not quite good enough. And the weird thing about that, that's a little hard to understand, is why we're getting such different numbers from our capture as from here. You know what I mean? And part of that could be, I don't know, like to what extent the GPU is messing with us, right? That's a kind of a question I don't actually know. But let's see here. Hello? Does not seem that I can actually toggle to Nsight, unfortunately. Nah. There we go. Good enough. All right, so in here, looking at Nsight just to see what the actual status is, like, I'm not sure what I'm looking at here. Why is this not shown? I want to see the actual frame profile, which this should be, but that doesn't look right. You know what I'm saying? Because if it should be more than 9 milliseconds, right? I mean, at the very least, it should show me like us spending time as well. But it doesn't appear to at the moment. Show me more, please. That is the range profiler. So all I really wanted to know is to what extent are the graphics causing us issues? Let me just do one other thing, because this is easier than trying to figure out if NVIDIA is giving us bogus information or not. This is always the way with modern computers, is you're just kind of swimming in a sea of probably wrong information, trying to figure out which one of it is right. So if we just open a like low res window, right? Like, you know, like that. So it's just super low res. To take some of the heat off the graphics card, you know what I'm saying? How fast are we then? You know what I mean? And I don't know. And so that would be a good thing to ask NVIDIA as well. If we're the same speed, then we know that it really doesn't matter, like, hopefully, which is presumably the case, but we haven't optimized our rendering at all for the graphics card, so it's possible that we've also got cruft in there, right? And I don't know. Okay, so at least in theory, and who knows, but at least in theory, it's us who's taking the time, right? And, you know, at least as far as I can tell, that seems to be the case, because that's dropping the resolution dramatically, and I'm not seeing a difference in frame rate there. So you know, at least as far as I can tell, it's not that. Now, I don't actually know, because the transfer time, like how long it takes to get things down to the graphics card, could be an issue for us right now. So don't actually know that that's true. I can't say for sure, but at least I know that like the pixel shader isn't a problem for us, right? Not on this card anyway. All right. So, and I guess there's one other thing I can do too, which is in the lighting system, I could just not compute it, right? So here, I could do this. And that would just turn the lighting off, the actual expensive part. And so here's us, you know, walking around in the dark, right? And let's take a look at what that is. That should be a lot of frames per second, right? So that's locked 60, right? So good. Because nothing else is happening there, meaning we are still running the full render pass. We're just rendering it with garbage lighting. So at least in theory, that should mean that if we get the lighting running fast enough, we would be 60 frames a second, right? And we're not blocked on anything else. I mean, we still would want to fix a bunch of other things, but, you know. So, all right. So that seems fine, and yeah, I mean, that seems totally fine. Yeah, so I think we're good there, and let's do one last test. If I go to the Raycaster, and you can see us doing our raycast here, where we do the two of these. If we so Ray Bundle Linux, we just do one pass over the sphere each time. So if I turn back on the tiles, for example, which we had turned off, so there's like a checkerboard pattern, right, that you can apply here. So in full cast here. So in here, if we want to, we can turn back on the checkerboard, which would reduce the number, and that should do 60 frames a second as well. Oops. Again, just trying to validate the fact that nothing weird is going on here. So if we do the checkerboard rendering, the checkerboard lighting, we can hit 60 frames a second sometimes, but not always. And it looks like it's whether or not we're moving, which may have something to do with how we're updating the lighting grid, or just where we are. Like that one, you can see is much worse, right? Not 100% sure why. Probably because there's more geometry in here, I would guess. but it's clear we can hit 60, right? So it's clear we can hit 60. The question is just getting there without having to do those shenanigans. All right. Okay. All right, so that's all good. Which brings us back to trying to structure a loop for better KD processing, which is a little bit of a brain bender. But let's keep at it. So, oops. So let's take a look at Raycast here again. There we go. So in Raycast, trying to work backwards, we know we're going to have something that looks like this, right? In here. So we know, don't need a second for a loop. So we know we're going to use this leaf index loop here. And we're going to use this to go over our actual AABBs to produce our ray collision tests here. So I think working backwards from there, assuming it's not a leaf container, we know we have to keep walking down the close side of the tree. And just all we're doing is making a stack of our far side of the tree, right? So basically, like, whatever the current stack value is going to be like the close side index, right? So whatever we're going to do on the next loop is just, we're just going to keep walking down that side of the tree. And we're just going to leave a stack around that's the far side, right? So then all we need to do is say, well, when we say like, oh, whoops, like that's not actually a thing, right, that we're doing. When we say, look, this thing doesn't need to be processed, the thing we're on does not need to be processed, then what we need to do is pop the stack at that point, right? So we just want to do a walking back up the stack. So while the depth is greater than 0, we just want to keep doing like a depth, minus, right? We want to do like a cur stack value thing. And we want to like figure out whether this thing is actually working. You know what I'm saying? Like, figure out whether we actually can use it or not. So if the end side bit, like if it can be used, we break, right? So I think that's how that would work. It's still not quite right. So when we need to decide like what the primary, like you can rearrange this loop in so many different ways because the things that have to happen can be placed in any number of locations, right? When we're actually going to process one of these things, what we're really doing here is just determining which side we're going to process, right? And so maybe what you would say is, can we make this primal? And I don't know if we can. So let's suppose we made start side primal, and then we said, okay, we're going to process the close side, right? So we then say, look, if the close side is a leaf, so we say, yeah, classify which side we're on. If the close side is a leaf, you just process it, right? And that's fine. If it's not, right, then that's your new then that's your new cur stack value, right? Yeah. All right, I think we're getting a little closer here. So if the closed side is a leaf container, then you do it. If of course, the problem is then you're never going to process far side leaf containers. So no, that would not work, right? So if you're actually doing close side and far side, yeah, that wouldn't work at all. I'm not really sure how to build this loop. So this is complicated enough that it seems like what I need to actually do if I want to do it right is I'm going to have to basically do each individual thing, write it out completely. So here's what I do in every single case, and then literally just compact those cases. I think that's the only way I can really do it. I just can't think of another way to do it. You know what I'm saying to you? Because I've tried, like, you know, being slick about it, and I can't seem to get it together, right? It doesn't seem to work. And so I feel like, yeah, like nothing I'm going to do there is actually going to help me, right? I don't know how we got into this state exactly. No, that goes there. I think that goes there. There we go. So I think I'm gonna have to. I think I'm gonna have to do something simple. I mean, something simpler at first, but much more verbose, and then try to compress it down into place because. So I have several problems, right, that I have to solve. So for every split plane where we have something that looks like this, we've got the following cases. So the first case is this, right? So here's like A and B. So, and you know what? Let me do this a little bit differently. Let's do it like this. A, B, case 1. Right? Then I've got case 2. A and B. Right? Then I've got case 3, which is A and B. Oops. Then I've got case 4. Right? And the nasty thing about this is there's actually 2 cases. Like, there's case, like, the 2 and 4 actually give rise to 5 and 6, which is to say that whether or not you've traversed this or not, right? So this moves backwards over time, and you may end up, like, another way to say it is there's a 5 case, which is that you were 2, but then you become 1. And here you were 4, but you become 3. Right? And the reason for that, again, is that if I have this case, and so I think it's a case 2 where I process A and B, when I go to process A, I may find that my close hit was like here, and then I now no longer need to process B, even though when I looked at A, I did. Right? And so that's why I say that that kind of needs to be a deferred thing. So the stack needs to push B on there. So when we go down, what we're effectively doing is figuring out which side we're on. Is it A or B? And pushing the other side onto our stack. When we then go to load the thing off the stack, then that's when we need to... when we load something off the stack, that's when we then need to test it, right? And that's why I was trying to zero in on something where we walk up the stack here, right? And so when we're walking up the stack here, we're looking for one that we can then start to descend again, right? Does that make sense? So it would seem like this needs to be, you know, I don't know. It's this sort of thing where we say, like, look, if this thing is a leaf container, and, you know, there's another way we could do this. We could just make this be like, look, everything has some boxes. So there's just a box count, right? And this, you know, it's like that, right? So everything has a box leaf count in it, and we loop over the leaves doing those as a thing. And a lot of them just have 0 because they're internal, right? They're actual just nodes that classify things. So then we have to do, like, okay, after we process anything that actually was leaf-like in here, then we have to go through and just determine who's getting processed and who's not getting processed, right? So, although, you know what, maybe now that I think about it, I guess we don't really need to do that because we need to know the result of that if anyway. So we're going to be stuck doing 2 ifs here, whether we like it or not, right? Which is unfortunate. Now, what we can do is we can help it out a little bit here by putting this branch, by making a little bit less of a branch here, because we know that we're always going to have some children. Otherwise, we wouldn't have continued down here. So what we can do is we can make this be a do while loop so that we only have the branch at the end, right? Rather than the branch at the beginning as well. So we can do this if we want to. Right? So that there's no branch at the beginning, because you know once you hit this branch, we don't need to do a second branch because we know that this thing should always have children. Otherwise, it wouldn't have been a leaf node, right? If it doesn't have any leaves children, then it wouldn't have had its bit set, right? So when we do this branch and we know, like, look, is this a leaf container? Then after we figure out whether it's a leaf container, we need to do this nonsense, right? Let's try to line this up here. So we check to see if it's a leaf container. If it's not a leaf container, then we go into the else clause where we try to do the classification. Once we figure out what the classification is, we push the wrong side, like the side we're not going to do right now, right? We push that on the stack. Yeah. Man, this is brutal. We push the wrong side on the stack, then we process the correct side, right? Because we know this is now a splitting region. So if it's a splitting region, then, as opposed to another kind of region, so then we do this. We then say, all right, we push the sides on correctly, and off we go. Right? But wait, so what's the case where we actually don't descend? So the case where we actually don't descend is actually the leaf case. Interesting. So I think that's correct, right? So if we're on a leaf, we do that work, and then we walk the stack to find the next person we can start treating as a region again, right? So the first time we find someone who actually passes that test. And then if it's not a leaf container, then we actually just do the classification on it and we split it. Right? So I think that would be roughly the way to do this. I mean, I don't see a lot else in terms of, yeah, I mean, it seems like it. I don't know. Right? In other words, you check to see if this is a leaf container. Assuming it's a leaf container, you do everything in the leaf container, and then you hunt up the stack to see who the last, what's the last thing on there that you need to check to do, right? Seems plausible. You then just see, like, yeah, is this thing... Because we know all the things on the stack were things that were far sides. We just see whether or not the far side thing that you're grabbing out is actually reachable. If it is, you stop, right? And you do the work. So, right, if this is reachable, you stop. Assuming that you weren't a leaf node, all you do is you classify and descend, leaving behind you, like breadcrumbs, all of the things you didn't process so they can be checked later by this side of the routine. If I'm understanding that correctly and not totally screwing it up in my head, that actually does work out to be pretty simple at the end of the day. Right? And there's no dependent pushes. So you push always. So if you didn't do a leaf process, you always push. And all you're doing is determining which one you're pushing versus which one you're using. So I don't know. That seems really straightforward. After I've kind of gone through it more carefully. But is it? Right? This is a good question. So you always need to load those, and I want to say you don't need this test mask. So what I think is you would basically say, all right, I'm going to select which one of these I do using the mask, which is basically just telling me which dimension I'm picking. I adjust using the plane D. I then know, looking at the sign, which side I'm on. Am I on the positive side or the negative side? So I know that we have a mask extract in here somewhere. And it's just any true, I think, or all true, or something like this. Any true. So here we've got like a move mask, right? And the move mask is, you know, it's a little bit deceptive. So what I want to do is basically say like, to extract like the sign. And the move mask will do that. Because I believe it always extracts the high bit, which happens to be the sign bit. So I can use this here. So because this is classifying the origin, I know that I only need to know just that one move mask. This could actually be done just entirely in float. So it's really all SS instructions, not PS instructions, but yeah. So if I just do like sign mask or something here, or like sign of the, I mean, I really only need the sign of the base value. So, you know, it's like, so if I take start side and I do a move mask on it and I just say like, look, I want to do an and, I want the sign bit, so it's going to be like, you know, that on the floating point value, but I believe this goes by bytes, so it'd just be the fourth bit, presumably. So that'd be the 1 bit. So really, I mean, this, right? Right, that's 0 bit, the 1 bit, the 2 bit, the 3 bit. I want to say it'd be that. And since I really guess I want to do it where I just shift this down by 3 instead. We'll double check all this in the docs. But I just want to extract just the sign bit from the first one, right? So I extract that and I just say, hey, yeah, so push 1, keep 1, right? Is all I need you to do. I just need you to push 1 and keep 1. And then when I need to do my other loop, which is the opposite way around, this one is looking at whether the end side gets in there or not. We know the start side is not on the same side as this. So we just need to know whether the end side makes it there or not, right? Is the way this would work. So the exact same code would work. The only difference is we need to do an extract on everybody, and then we're just going to test for truth, right? So in here, we would just say, okay, the start side or the end side bit here is a mov mask, and we just want to AND it with whether or not any of these would be the case. So after the move mask happens, we just look at the sign bits of anybody. So those sign bits are going to be like the, in hex, each one of these is 4. So the high bit on each of these is what we would want, assuming that that actually is what that is. I don't actually know if that's true. So we'll have to go look at that. But this basically means that somebody needs to... one of the rays can reach it, of the 4 rays we have, right? So at that point, the only thing we need to do is actually be able to load this crap out of the value we have, which is this, right? So what are the things we actually need to know? Well, the things we actually need to know there are literally just these values. So we need to know a Y mask, a Z mask, a plane D, and, you know, if you look at what this actually entails, it's pretty basic, right? So I don't know what the fastest way is going to be to do this, but it's going to be pretty straightforward because we can pack literally everything into a U64, I would think. So if we did something like this, or we actually don't even need that. I mean, this could be these could be 16-bit values that we push on here. Yeah, anyway. So I don't know. I mean, in theory, this actually works. How good do I think it is? I don't know. But in theory, this would actually work. And this is trivial. Like, this is, like, really very little code. This does one check, but has to do 2 loops because it has to do the stack walk. And that seems bad, potentially. But I'm not sure what else you would do. So, I mean, I think this is what it looks like. So I'm going to leave that off for now. And that's what we'll work on next week, I guess. We'll go to brief Q&A. So, yeah, now that I'm looking at it, it's getting better, right? Like, it's not as bad as I thought it was at first, if this is actually the right thing. I do feel like this part of things... This part seems like it's probably sort of wrong, maybe. And the reason I say that is, again, it's not using all the lanes. It should be, and it's not. So I don't know. We'll see. Anyway, we'll go ahead and do Q&A. A little Q&A here. But I'm okay with it. I'm okay with that. And, you know, oh man, Insobot. Instabot wins the Q&A already. Is this PHP? No. It's C. PHP, like many languages, borrowed C's structure. So it looks, PHP does look like C to a certain extent. Is there a good way to get intuitions about bitmasks, etc., or is it just practice? I mean, bitmasks are actually pretty simple. It's usually more the fact that you write them in hexadecimal oftentimes that makes it more complicated. I mean, there's just 32 or 64 lanes, and they're either set or not set. So you're just thinking of these little like lanes that come in, and you know what do you want to happen with the individual bits and moving them around. It's not that bad, right? The only thing that I was saying here is for move mask, I just always have to refresh my memory to what it moves. Because there's a lot of ways they could have chosen to do that, and I think they chose the smart way. But if you take a look here, so like the move mask PS, so that's that. If you do the move mask PS value here, you can see what it says. It says the most significant bit of the corresponding packed single person floating point element in A. So I just didn't know which one it's doing. So let's see. What does it actually say? Okay, so actually, it's not even as bad as I thought it was. It's actually even easier than I thought it was. So actually, all we have to do is this. It's actually just moving just the high bit of the 4 values. So it's literally just this. Right? So I just couldn't remember what move masks I had available, because if you think about what this is doing, you have 128 bits. That's the register you're actually talking about. So the actual value inside the CPU is 128 bits. We're using that to compute 4 separate floating point numbers. So 32 bits, 32 bits, 32 bits, 32 bits, right? 4 times 32 is 128. And I want to know the sign of each of those 32-bit values. Well, the sign bit of a floating point value is the highest bit. It's bit 31, right? Or bit 32 if you're starting with 1. So swinging bit 0 to bit 31, it's the last bit. It's bit 31. So I didn't know what move mask did because there's different ones. So I remembered this one. I was like, well, move mask EPI 8, that moves the high bit of each byte, right? So you can see this one. So if that was the move mask, and I couldn't remember what it did, but if that was the move mask, then I need to go 4 bits in to get the sign bit. But because I actually have a move mask PS in this instruction set, I'm just only getting the sign bits. So I just have a 4-bit value where each bit is the sign bit. So it's actually much more useful, right? Do you write shader code often for work? Not often, no. I try to keep GPU programming to a minimum because it's always really janky. Like, GPU programming just sucks. I mean, GPUs suck. They're not, I don't like them. Like, I wish we didn't have to have them. I wish we just had CPUs that were fast. Or just people didn't have GPUs, so you didn't have to use them. You could just write software renders and be done with it, you know? Do you sometimes feel the urge to make Handmade Hero truly 3D? I mean, it's a lot easier to be all 3D in the code. So the code for doing all 3D in the runtime is way easier than 2.5D. Like, way easier. So that part is nice. But the problem is your asset pipeline becomes a massive nightmare. So as soon as you go 3D, you 10x the work of your asset pipeline. Just Massively, massively. You have to have like a bone system, an animation system, and like packing that down and fitting it from the art tools. And you got to have texture mapping and UV coordinate assignment and all this stuff. So your runtime gets a lot easier than having to deal with the 2.5D stuff, but your asset pipeline becomes a massive, massive nightmare. Not to mention now you have to have 3D artists instead of 2D artists, and they have to do stuff, and you have to decide how you're building those assets. Are they going to be high res that can project onto low res? They're just going to build low res directly, or are you going to use bump maps or normal maps, displacement maps, blah, 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 right? And if you use a commercial engine, someone's saying your asset pipeline becomes Unreal Engine 4. Exactly. If you go look at how much cruft there is in something like Unreal Engine or Unity or that stuff, the actual renderer part of the 3D is not where all the cruft is. It's the huge, giant thing that has to sit there to get stuff into it, right? And so it's always a trade-off where you're like, look, if you can get away with 2D, yeah, it's a little more annoying because you got to do these tricks at runtime to figure out how you're going to actually render something attractive when you don't have the data you need. But that expense is small compared to the expense you will pay in the pipeline if you decide to go full 3D. It's the pipeline that kills you on 3D, not the renderer. The renderer is easy. I mean, it's not easy, especially if you've never done one before, but it's not anywhere close to as hard as the pipeline in terms of sheer, like, man hour. Like the time it's going to take you to build the thing, you're going to spend way more time dealing with your asset pipeline than you ever are going to deal with your renderer. I'm a bit behind in the vase. Do you ever trace secondary rays that bounce off in random directions that might lead to incoherent ray packets? Nope. So the way we get around that, because we do have fully infinite bounce lighting. Like we don't have any, it's not infinite bounce. It's 100 bounce lighting or something like that. I don't know how you want to classify it. But the way we get around that is we actually just convect. So we shoot out rays from our sample point and we gather the light and store it for next frame. So we're like a bucket brigade, right? So we do the secondary bounces for the previous frame that were caused on the previous frame on the frame after, right? So it's basically like just over time. And so the result is we get a little bit of lag in the secondary bounce, tertiary bounce, like the more bounces, the more lag, but we never get ray decoherence because of that. Does that make sense? Can't C++11 use something like OB1111? Yeah, it can. Yeah, I never do, but they introduced a bunch of stuff. Here it is. So originally C only had these: decimal, octal, and hex. This one, it looks like it says C++14, so it's actually not C++11, but it looks like C++14. So if you want to rely on the fact that you have a modern compiler, you can use this. And then it's just like, 011, 0111, 0111, right? I don't do that because I try to avoid using things in the C++ spec, especially new things, because the C++ spec is a disaster, and I want to be able to write my own compiler for my code and not have to worry about 8 billion stupid C++ spec things that are useless anyway. So I just try to stick with basically C, and I find that operator overloading is really important, so I use it just to make the code legible in math. But I generally just don't start using things that are adding entire like Lexler things or whatever. And not that this is hard, like this is not hard to add to your Lexler. It's super simple, but it's just like, I don't want to like necessarily wed myself to their notation or any of that stuff. So I'm just like, look, C is fine. C++ is just a waste of everyone's time. It doesn't save you time. It's just a bunch of crap you can learn and then it makes your code worse, right? So I just say like, no, forget about it. C is fine. And it keeps the code simple so that when you want to go move off to some other language, which you will want to do because C++ is garbage, it's easier to port that code because you're not using all this weird C++ nonsense. In an IAM GUI situation, how do you create a unique ID for a UI control? What I don't get is if you draw everything immediately, if some condition changes, won't the ID also change? So if you want to use IDs in any API, it doesn't matter whether it's IAM or not. The rule is just you need some way of assigning IDs. And the point is that the app itself is the thing that should assign the IDs. It doesn't matter how you assign them. If you want to assign them using allocation, which makes your thing basically a retained mode GUI, you certainly can. Just don't put that in the library. Let it pass the ID forward. Usually you can though, because usually whatever the logic is that you use to draw the control, it's got to go do something like modify a particular value or something that has a unique ID already, and you can just use that. So usually it's a win, right? Has Handmade Hero gone as planned, or did you not have any expectations or scope when you set off on the journey? I didn't really have any expectations or scope, but I was going to be only 2D originally. So the main thing we did differently was that it's got a full 3D render with lighting, which is a pretty big add, but that's the main thing we did differently, I guess. How many % is Handmade Hero done? I don't know. The engine's almost finished. We basically just have some cleanup to do after the lighting is done, but the engine's basically finished. So it's really just the gameplay, which will be sort of open-ended, like how much gameplay we want to pack in this thing, I don't know. I'm not really a gameplay person. I'm not a designer, so it's not my thing. So I don't have any concrete, like, it has to be this way stuff. So we'll see. It's unclear. Would you consider moving Handmade Hero to JI when it releases? Probably wouldn't necessarily move it to JI. If I was going to do JI, I'd probably want to just try something in it first. Like, I'd probably do something new in it first, right? Like, just a small thing just to see. All right, let's go ahead and wrap it up. All right. Thank you, everybody, for joining me for this on Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along with the series at home, you can always pre-order the game. It comes with a source code so you can do your own experiments. I sketched out what that KD tree thing needs to look like. So over this next week until I'm back next week and to work on it, that might be a good thing to play with. For those of you looking for a challenge, try to do your own KD tree, do some timings on it, see if it's better. Does it actually improve our performance or doesn't it? I think that'd be a great thing to practice on, right? So give that a shot. For those of you who are interested, we're also doing a Kickstarter right now at Molly Rocket for our comic. We're doing a print run of it. It's going to be pretty cool. So if you want to check that out, the banner's at the top of the handmadehero.org page as well. So you can just click on that. It's got all the information there. That's it for today. I'll be back here next week when I'll take a look at implementing that KD tree stuff as the way that we sort of worked it out today. And we'll go from there. I will probably now switch over to my streaming machine to see if John is streaming. He's been streaming a lot lately, and we will go dump everyone into his stream if he is on again, which I don't know if he is. So I'm gonna go check. and see if he is. Raid channel, Naysayer, 88. Nah. Unfortunately not. So I guess we won't be. So that's it for today then. You'll have to find your own stream to go to now. So until next time, have fun programming, and I'll see you on the internet. Take it easy, everybody.